this uses circular motion and relative motion. Okay, so if you choose a coordinate system with the y-axis pointing directly out of the surface, so for example, if the thing's rolling along a horizontal surface, the y-axis is like this. That means the x-axis is like this. And if the surface is that, then we're going to use a coordinate system with the y-axis this way and the x-axis this way. And if it's like that, then the y-axis is going to be this way and the x-axis is this way. Okay. And this is the center of the wheel or the ball or whatever is rolling. Then the velocity of the center of the thing that's rolling is going to be negative omega times the radius of the thing that's rolling for the x component and 0 for y. And the acceleration of the center is going to be negative alpha r and then 0 for y. So any rolling without slipping problem, you're going to use these equations. And those are derivable using the relative motion equations. I'm not going to go into the derivation, but I'm going to show how to use it with relative motion. Question? Okay. All right, so let's say that, let's say this is horizontal. And you have this wheel rolling with an angular velocity this way of, let's say, 2 radians per second. And let's say it's speeding up with an angular acceleration of 10 radians per second squared. We know it's speeding up because those are the same direction. And the radius of this wheel is 0.5 meters. The center, let's call that C. The point at the bottom, let's call that B for bottom, and then at the top, T. Let's figure out first what's the velocity and acceleration of C. Then let's figure out the velocity and acceleration of the top. And then the velocity and acceleration of the bottom. Okay. So the first part of this is just using the using the rolling without slipping equations to calculate the velocity and acceleration of the center. So the velocity vector of that point C is just going to be, and our coordinate system is going to have the y-axis straight out of the surface, x-axis horizontal. Okay. Because that's the coordinate system we're always going to use for this. Okay, so the velocity of C is negative omega r, and then 0 for y. What's omega in this example? Yep, positive 2 because it's counterclockwise. So this is positive 2. We have the negative sign in front of it, times the radius, which is 0.5. And so we get a vector of negative 1, 0. This is a velocity. This is meters per second. Or you could think of this as the velocity is in this direction with a magnitude of 1 meter per second. So if this is rolling, does it make sense that the velocity would be in the negative x direction if it's rolling counterclockwise? Just intuitively. That has to be the relationship unless there's sliding at that bottom point. We're not considering that. So that direction makes sense, right? What direction would you expect the center of this wheel to be accelerating? It's also going to be in the negative x direction because we know that it's speeding up. Okay, we know that the rolling is speeding up because the two angular quantities are in the same direction. Okay, so that means that the translational acceleration of the center also has to be in the same direction as the velocity vector. So the acceleration of the center is negative alpha r 0. So that's negative of, we have positive 10 for the angular acceleration. Times 0.5, that's the radius, and 0. So we get an acceleration of the center of the wheel of negative 5, 0. And this is meters per second squared. And so you could also think of this as a vector in this direction with a magnitude of 5 meters per second squared. So if this was the wheel of a bike or a car or something, this is how fast the actual vehicle is going, the cab, you know, or the seat or whatever, because all that is rigidly connected to the center of the wheels. Okay. All right, so now let's think about how to calculate the velocity and acceleration of the top. Okay. Well, what we want is the velocity and acceleration of the top relative to the ground. Okay. If a problem doesn't specify what something's relative to, it always means relative to the ground. So how can we do this with the things that we know how to solve? Well, the velocity of the top relative to the ground, we can think of using the relative motion equations as the velocity of the top relative to the center plus the velocity of the center relative to the ground. This one is what we just calculated. This one comes from the rolling without slipping equations. Okay. This one, so now imagine that you had a camera, a coordinate system that was fixed, that was moving along with the center of the wheel. What would it see the other points on the wheel doing? It would just see those points moving around it in circular motion. Do you see that? Okay. It wouldn't know that it's moving. It would just see the points going around it. And so this is just circular motion. Okay. So now we have a part that comes from rolling without slipping. We actually already did that in part A, so we don't have to do that again. We can just bring in the values we got. And we have a circular motion part. And then we just add those two parts together and it'll tell us the velocity and acceleration of the top. Anyone have any idea, any thought on, so think about first the velocity of the top. Anyone have any idea what the velocity of the top of a wheel is doing compared to what the center is doing? It's moving at 2 times, so the speed of this is twice this. Okay, that's what we're going to see. And actually, if you take a picture of a bicycle wheel using a slow enough exposure, you have to get the exposure like exactly right to show this. But what you'll see is that the spokes up at the top are really blurry, and the center is relatively crisp. Everything, as you get closer to the top, is moving faster and faster until it's going twice as fast as the vehicle itself. Okay, so let's see how that works. So this we got in part A. We're just going to add that on at the end. So what we have to do is the circular motion. So we want the velocity of the top relative to the center. And to do that, we're going to think of a circular motion where this thing is moving with, what did I say, the angular velocity is 2. So there's an angular velocity of 2 radians per second and an angular acceleration of 10 radians per second squared. And we want to figure out what's going on at the top. We know that the radius is 0.5 meters. Okay, what do we know about the directions of these vectors? So we're treating it like the center is still now. What's the direction of the velocity vector of that point at the top? It's to the left. It has to be tangent to that circular path. Okay. So there's the direction of the velocity vector. I think I'll just leave it like that for now, but normally we draw the velocity vector, then we draw the tangential acceleration, centripetal. I'll do those when we get to acceleration. Okay, so the magnitude of the velocity, the speed, we're going to use the circular motion equation that says we take the absolute value of the angular velocity and multiply it by the radius. And so that's 2 times 0.5. So 1 meter per second. We know that velocity is in the negative x direction. And so the velocity of t relative to the center is -1, 0. Okay. And now put it together, the relative motion equation says the velocity of t relative to the ground is equal to the velocity of t relative to the center plus the velocity of the center relative to the ground. That's -1, 0 from the circular motion plus the velocity of the center relative to the ground that we got in part A. And so you get a velocity vector of -2, 0. And we know that the acceleration of the center is all in the x direction, and that's -α_r, 0. And then we use two relative motion equations. So I'll just write those as VAC is equal to VAB plus VBC, and then the acceleration version. And what we figured out so far is that VC is -1, 0 meters per second, and AC is -50 meters per second squared. And then we used relative motion to calculate that the velocity at the top is -2, 0. That velocity is always going to be twice the velocity of the center. And so now we want to calculate the acceleration of the top. And the velocity and acceleration of the bottom. Okay, well, to calculate the acceleration of the top, the process is about the same as calculating the velocity of the top. We're going to use the relative motion equation that says acceleration of the top relative to the ground is equal to acceleration of the top relative to the center plus the acceleration of the center relative to the ground. This one is this. And this one is circular motion, assuming that the center is fixed. So ignoring the motion of the center and just doing the circular motion. All right, so to calculate the acceleration of the top relative to the center, let's think about that circular motion. So we have this thing that's moving this way at 2 radians per second and 10 radians per second squared. So we know the velocity direction is this way. What direction is the tangential acceleration? The same as the velocity, because you can think of it as it's speeding up because the two angular quantities are the same direction, or you can just recognize that if the angular acceleration is this way, the tangential acceleration has to be tangent to the circle in that direction. Okay, so this is the tangential acceleration. The centripetal is always toward the center. And now we can calculate the magnitudes of those. The magnitude of the tangential acceleration is the absolute value of the angular acceleration times r. So that's 10 times 0.5. So 5 meters per second squared. That's in the negative x direction. So the tangential acceleration vector is -5, 0. The magnitude of the centripetal acceleration is omega squared times r. So that's 2 squared times 0.5. So 2 meters per second squared. That's in the negative y direction. So the centripetal acceleration is 0, -2 meters per second squared. And now we can put those together and we get that the acceleration of the top relative to the center, okay, that's the one that we're getting with circular motion, is equal to -5, -2 meters per second squared. So that means that the acceleration of the top relative to the ground is equal to the acceleration of the top relative to the center, what we have here, plus the acceleration of the center relative to the ground. That's -5, 0. And you get -10, -2. Any questions about that? Okay, so now we're going to do the same thing for the bottom. It's going to be the exact same approach. It's just that where at the top, we'll see when we use, yes? I plugged in -5, 0 for, yeah. Okay, so at the top, we saw that when we use the relative motion equation, the acceleration and velocity of the center and the acceleration and velocity from the circular motion were in the same direction, so they added, and that's why we got that double size on the x components of these things. We're going to see when we use relative motion for that bottom point, they're opposite directions, and so they offset each other. And what we're going to see is that the horizontal velocity and the horizontal part of the acceleration of that point are 0 at the bottom, which makes sense if you think about what it means for the wheel not to slip on the ground. If the point in contact with the ground doesn't have the same horizontal velocity and acceleration, that means that the wheel is slipping at that instant. Okay, so at that instant, the horizontal part of the acceleration and the velocity have to be 0, and that's what we're going to see. So right at that instant, it comes to a rest and then starts moving again. Okay. So now the bottom. For the velocity, we're going to use velocity of the bottom relative to the ground is equal to the velocity of the bottom relative to the center plus the velocity of the center relative to the ground. We already have this. And this one, the velocity of B, assuming that C is not moving, is circular motion. Okay, so let's think about the circular motion. It's going this way, that's the angular velocity and the angular acceleration. And so at this point D, the velocity has to be this way. Which direction is the tangential acceleration? Same. And the centripetal is toward the center. So we know the directions. Now we can figure out the magnitude. The magnitude of the tangential acceleration is absolute value of alpha times r. So that's 5. It's in the positive x direction, so the tangential acceleration vector is positive 5, 0. The centripetal acceleration magnitude is omega squared times r. So that's 2 squared times 0.5, so 2. And we know from this picture that that's in the positive y direction. So the centripetal acceleration is 0.2 meters per second squared. And so the acceleration of B, assuming that the center is fixed relative to C, is 5.2. Okay, so we'll use that in a second. And let's figure out the velocity vector too. the magnitude of the velocity is the absolute value of omega times r. So that's 2 times 1/2, so 1. And the velocity is in the positive x direction. So the velocity vector of B relative to C is 0, 1. Nope, 1, 0. And now all we have to do is put those together with the relative motion equations. So I'll do velocity first. So the velocity of the bottom relative to the ground is the velocity of the bottom relative to the center plus the velocity of the center relative to the ground. That's 1, 0 plus velocity of the center relative to the ground. We got that last time, is negative 1, 0. And so just at that instant, when the object is at the ground, the velocity is 0. And then the acceleration of B relative to the ground is the acceleration of B relative to the center plus the acceleration of the center relative to the ground. Acceleration of B relative to the center is positive 5, positive 2. Last time we got that the acceleration of the center is negative 5, 0. And so the acceleration of the bottom is just 0, 2 meters per second squared. So at that bottom point, the velocity is 0. It's instantaneously at rest. And the horizontal part of the acceleration is 0. Those are the things that are required for the bottom not to slip against the ground. Okay, and that's always the case with